So before introducing our speaker today, I wanted to say a few words about SZNet and what we are doing here. So you are this is the first webinar of our SZNet first virtual workshop. SZNet is the international component of SZ4D. It is a coordination network of networks. And we're working towards building an international community to study subduction zone geohazards, specifically to define the limits and possibilities of predicting geohazards. And the three main missions of SZNet are to compare observations of subduction zones around the globe, with common data sets and understanding, to cooperate to consistently instrument critical subduction zones that can provide us with key and transferable insights, and to develop and nurture an international and diverse cadre of early career scientists that are equipped to make the necessary breakthroughs. And we welcome feedback from all of you. Here there are two links that will also be shared through the chat. The one on the left is for you to suggest any workshop topics and speakers. And the one on the right is an optional anonymous demographic survey that we very much welcome you to fill. So with that said, today we have the great pleasure to have our first speaker, Demian Saffer. Demian is a professor in the University of Texas at Austin. He's also director of the Institute for Geophysics, and he holds there the Scotty Petty Jr. Endowed Chair. He was formerly the head of the Geoscience Department at Penn State University. He graduated in 1999 from UC Santa Cruz. His research covers a broad range of topics and methods in active tectonics, especially for subduction zones, where he studies fault and sediment mechanics and deformation, friction, including the role of fluids. And he is also very much involved in development, Pore, instrumentation, ocean drilling projects. The excellence of his research was honored in 2002. He was selected to give the AGU Birch Lecture, which is the highest honor in tectonophysics. And he's been involved in SZ4D, notably through the working group on faulting and earthquake cycles. And prior to that, he's had leadership roles in past initiatives such as Margins, GeoPrisms, JFAST. So we're very pleased to hear from Demian Saffer today on pore pressure, stress, and friction along megathrust. So Demian, the floor is yours.
All right, thank you, Pablo, for a really nice introduction. Thanks, everyone. I'm looking at the number of people who are here. It's outstanding. So thanks, everybody, for taking part of your Monday morning or Monday afternoon or maybe Monday evening, I guess, depending on where you are, to hear from me. Can everybody see the slides, or maybe somebody can just give me a thumbs up, Pablo, or...
We see it, but not yet in presentation mode.
How about now?
That's not quite the presentation mode either.
We're seeing the speaker view.
Flipped.
Speaker.
Is that better?
Yes.
All right. Okay. Outstanding. Okay. So, yeah, I thought today I'd give a kind of, I don't want to say an overview, but try to touch on a number of topics pretty much in this order. So talk about different ways that we attack the problem of understanding fluids and fluid pressure in subduction zones. And of course, that's tied very intimately to stress and the stress state in situ. And then I'll talk a little bit, really, if you're a friction or experimental friction aficionado, I hope you're not disappointed. I'll talk a little bit about that kind of work. But there's so much to be covered in that arena that really just going to touch on a couple of focused topics there. So we'll jump right in here and just sort of point out, right, I guess these images were carefully curated here to kind of illustrate the range of things that I'll be talking about. And so it includes, for example, laboratory experimentation, And this is a picture of Robert Valdez doing triaxial experiments to understand sediment properties here on the right. Talk a little bit about friction, as I mentioned. This sort of bottom center panel is a model result, looking at how we might get at stress and pore pressure from numerical predictive approaches. This very photogenic photo on the left side here is a wellhead. So a lot of our data and samples come from ocean drilling, which gives us access to the shallow, at least the upper kilometer or two of these systems. So yeah, all right. Okay. So, one of the things that I think many folks here may already know is that over the last roughly 20 years, there's been kind of a revolution in our understanding of faulting and earthquakes and particularly subduction zones. And the key observation, right? So if we go back now, what is 27 years, on the top left here, there was a kind of simplified way of thinking about subduction zones and subduction zone earthquakes, that there was a so-called seismogenic zone that might start at something like 5 to 8 kilometers vertical depth, and then that would extend to some depth below which you hit the brittle ductile transition and rocks behave more plastically. And so there'd be a transition into something where you had essentially viscous behavior. So you had a zone that was capable of producing earthquakes, and it's bounded at its shallow edge by materials that are soft and porous, like sediments, typically clay-rich sediments. And something happens that turns on earthquakes at this depth and a temperature of about 150 degrees. With new observations, it became very clear that the situation in the picture is much more complicated than that. And so, roughly 15 years later, there's this sort of central image kind of shows the idea that there are observations of not just creep or stable sliding, but actually slow earthquakes, low frequency earthquakes, tsunami earthquakes, which are a particular kind of earthquake that slip fast enough to displace the seafloor and cause a tsunami, but are deficient in high frequency energy. So kind of a spectrum of slip behaviors surrounding and fringing this seismogenic zone where large, great, magnitude 8 class earthquakes might occur. And the same thing at the down dip, deep edge, where there is this sort of chatter of what's called the chatter of silent slip. So it's things like episodic tremor and slip. Fast forward another five or 6 years, and the picture becomes even more complicated, and it's now sort of recognized that even within the so-called seismogenic zone, it's patchy, right? And so in some cases, this whole thing might rupture in a very large earthquake. In other cases, it's partitioned into zones that are locked and others that are creeping even within that PT, pressure temperature space. And so this recognition of increasing complexity has raised all kinds of really interesting questions. And that's kind of the core of what I hope we can talk about today. And so these fundamental questions include things like, well, what controls this behavior? Why do certain parts of the fault behave one way and others behave might generate earthquakes rather than creep or host slow earthquakes? Are these behaviors, keying on this bottom right panel, are these behaviors things that are predictable and persistent over time? Is there something we could measure or observe to tell us what kind of behavior to expect? And then what are the mechanisms? What are the processes that control that? And so what that means really is needing information about what is the condition or the state of the material. What's the pore pressure? What's the temperature? What's the stress in these zones? And what are the materials and how do the materials behave? And so those are some of the questions we'll get at today, with a particular focus on the role of fluids and fluid pressure as part of that story. And the reason we care about fluid pressure, this is a little bit of a complicated diagram, but try to go through it. So in a very simple way, this is just a sort of a 1D way of thinking about the force balance that might control whether you have an earthquake or could nucleate an earthquake versus creeping along stably. And so the idea is that you can imagine, if you think about a force balance, you have force on the y-axis and displacement on the x-axis. If the fault starts to slip, when that happens, you're relieving some stress in the rock around the fault, or you're relieving some stress in the system. And that's kind of shown here by this dark black arrow. And that can only release stress as quickly as the stiffness of the material lets it, right? So if you have something that's really stiff, then a tiny amount of displacement drops the stress very quickly, and then you run out of steam. If something is very spongy, then it may only release a tiny bit of stress when it moves. And so the competition between how quickly you unload the stress that's built up in the system relative to how quickly a fault may get weaker as it starts to slide really governs whether you can nucleate something that's unstable. And so this is kind of a classic way of thinking about this force balance. And what it boils down to is a comparison of the stiffness of the system. So this is essentially how quickly you can unload that built up stress versus how rapidly the materials in the fault zone might weaken as they begin to slide. And so if it weakens very rapidly, then you can essentially have excess stress built up relative to how quickly you've weakened the material. And so then you get a runaway rupture. In other words, if the fault starts to weaken very rapidly as it goes faster and faster, then it'll weaken a little bit, that'll let it go a little bit faster, then it weakens even more, and so on. And you can get into a runaway nucleation of unstable slip. Alternatively, sort of the opposite end of the spectrum is that if it actually gets stronger, the faster it slips, then you'll quench anything that might try to nucleate. So anyway, this is kind of the framework that we use to think about this, again, in pretty simplistic terms. And you'll note, and again, happy to answer questions about this later, but for now, just to note that the rate at which the fault might get weaker as it starts to slide is controlled by a couple of things. One of them is the left-hand term here, which is the effective stress. So that's essentially, you can think of that as the clamping stress or the normal stress across the fault. The harder it's being squeezed together, the more it scales or amplifies any changes in friction as it starts to move more quickly. The other part of it is the frictional properties. And so that's shown here. So B minus A is really the change in friction, and D sub C is the distance over which that occurs. So you can think of this as almost like a frictional stiffness of the fault. It's a change in friction per slip. And so the product of these is a normal stress times friction is a change in shear stress per slip distance. So this is this idea that it could get weaker or in some cases stronger the faster it tries to slide. And just to back up, so the reason that we care about pore pressure is that the normal stress is counteracted by the pore pressure, or the effective normal stress is counteracted by the pore pressure. So that's shown here. And so that's sort of part A of this story. And then part B of the story is the intrinsic material properties. And generally speaking, high pore pressure or low stress tend to decrease this number, and that pushes these two things closer together. So that pushes you towards stable behavior. Likewise, a smaller number here in red would do the same thing. And so you can achieve slow earthquakes or a spectrum of slip or even stable sliding in this sort of framework if you have very low effective stress, i.e. high pore pressure, or if you have a transitional frictional behavior. And so these are, again, the two sides of this equation or the two sides of this coin that we're going to explore. And really going to focus particularly on the outer reaches, the shallow part of the plate boundary. And so what I mean by this is maybe from the trench back into the shallowest part of the seismogenic zone. So the upper 10 kilometers of the Earth's crust vertically, and what amounts to maybe the 40 to 60 to even 80 kilometers from the trench toward the coast. And the reason we focus on this particular area is really a couple of reasons. First, it's a place where we can drill into it and we can understand the materials really well. And part of that is also that we can image it really accurately. So it's much easier to get high resolution images of this shallow part of the system. And you can kind of see that here with seismic reflection image from New Zealand on the far left bottom. And in the center here is a seismic reflection image from the Nankai margin in central Japan. So you can see the detail of the structures and the properties of the materials really well in imaging. And so that makes this an area that's easy to characterize in detail and quantitatively. The second part of why we care about this outer part of the system is that this is a zone, as we learned, unfortunately, from the Tohoku earthquake in 2011, is a zone where it's the fault, the megathrust fault is host to hazards that we don't understand very well. And these include shallow coseismic rupture and tsunami generation. Okay, so let's talk about pore pressure. Well, we have lots of indications that pore pressure in subduction zones is elevated. Good examples of this are on the top left. This is actually an exhumed system from 12 to 15 kilometers depth in Alaska. This is a photo from my late advisor, Casey Moore, and his field work there. And you can see this veining along and around the what used to be the main plate boundary at depth before it was exhumed and uplifted on the island. So this veining implies that the pore fluid pressure was large enough to crack open the rock and to fill in that void space and precipitate quartz, right? So there's clear evidence for paleo pore pressures that are, at least at certain times, very high. We also have modern day evidence, and this is one of the coolest pictures I've ever taken, even though it doesn't look anything like something you'd see in National Geographic or in a calendar or anything. But this is actually a photograph of the Middle America Trench off of the Nicoya Peninsula in Costa Rica, taken from Alvin. And what you see is in the foreground is the Cocos Plate. And in the background here, where my cursor is the Caribbean Plate. And this little outcropping here is actually a 50 centimeter high ledge of calcium carbonate that's precipitated orthogenically. This is the trench. So you can actually drive across the trench and put your little finger, or you couldn't put your finger, but the finger of Alvin, which is a manned submersible, right on the trench. And the reason that this carbonate is here is because fluids are seeping out. And this is an indirect indicator that there must be high pressure at depth that's forcing those fluids to come out, right? So that's another sort of indirect indicator. So we know that pressure is high in these systems. But what we don't know, or at least is harder to come by, are quantitative constraints beyond just, yeah, pore pressure is kind of high in the subsurface. So that is, where is it high? Is it high along faults? Is this depicted in this cartoon? Or is it sort of high everywhere regionally in this system? And then how high? So what is the distribution and what is the magnitude? And those are really the key questions we need to answer if we want to understand the relationship between fluid pressure, fault strength, and slip behavior. Likewise, we know very little about frictional properties. And so here are some examples just showing different kinds of data. So what's shown in the top right here is an example of how we measure this slip dependence that I was talking about, whether it gets weaker or stronger as you try to go faster. This is a little velocity step. And so you're cruising along in an experiment in the laboratory at a particular speed, and then you change the velocity, and then there's some initial change in friction, and then a recovery to some new steady state value. And so we can measure this kind of thing in the laboratory as a function of composition. And so that's what's shown on the bottom is this is this A minus B term, which is the extent of the change in friction as a function of velocity, of sliding velocity. And so we can measure this. The different colors are different materials of different compositions. And then at the x-axis is the speed at which we're doing this experiment. And so a couple things sort of stand out here. One is that it's strongly dependent on the material that you have, whether it's clays or carbonates or quartz. And so there's a lot to explore here that we don't really understand. And it means that it's going to be different from one subduction zone or one fault zone in the Earth's crust to another. And then not shown here, another part of this is that another key component of how faults work is so-called healing or re-strengthening between earthquakes. And that's also something that is strongly dependent on composition and other factors, like pressure and temperature conditions. And so these are things we don't understand very well, but they're, of course, really important as the other part of the story in terms of controlling how faults may behave, whether they can nucleate earthquakes, whether those earthquakes would be slow motion earthquakes or rapid earthquakes. Okay, so what I'm going to do here is jump into sort of the first half of some of the results and examples from the talk and really focus on pore pressure. And sort of there are three parts of this. One is different approaches that we've taken to try to understand and quantify pore pressure and stress from laboratory measurements and also from drilling. Then talk a little bit about how we can extrapolate that to get a more regional picture using geophysical observations, and in this case, really focus on seismic reflection data to map stress and pressure in 2 dimensions or even 3 dimensions. And then talk a little bit about some insights that we can get from numerical models. Okay, so of course, the best way to measure pressure, if you can do it, is to just measure it, right? And so this is possible. But it's, as you might imagine, putting a well in and shutting it in and sealing it to measure pressure in the subsurface somewhere off the coast of a subduction zone in 3 kilometers of ocean depth, and then getting a well drilled and completing that well is a little bit more challenging than a water well on land where you might measure hydraulic head or water level. So we have a few of these so-called corks, which is the shorthand for these borehole observatories that provide long-term monitoring of pressure in subsea floor wells. And so here's the seafloor. Again, this is under the ocean. So sea level would be maybe a few kilometers above this. And then there's this installation drilling through the sediment in this case, and maybe into a second layer of either deeper sediment or the igneous ocean crust in this particular example that I'm showing. And so this is a way you can get pore pressure. I'll also come back to this because there's some other really cool things you can do with the time series, because you're not just monitoring a value of pressure, but how it changes over time in response to things like a strain or tectonic events. So I'll come back to that. But the real problem here is that we only have about a couple dozen of these on the Earth in total. So they're not going to give us the answer. They're just they're sort of the Cadillac way to do this, if you will. Okay. So another thing we can do is we can, at the same time that we're installing these observatories, or in other parts of the world where we're drilling boreholes and shallow subduction zones, we collect samples. And those samples give us tons of information in a couple different ways, right? So one way that they do this, and I'll kind of draw on this in the second part of the pore pressure story when I talk about seismic reflection data, is laboratory tests tell us about wave speeds and allow us to map between things like porosity or P wave velocity, which we can observe in the Earth, and turn that into predictions of things like pressure and stress, right? You can't do that without having some calibration. And so the lab provides that calibration. And then the other part of this is that we can actually do experiments to deform the samples, which tell us about permeability. That provides an indirect clue about how it might behave as it's being subducted and squeezed, and whether fluids can escape or not. And then the deformation behavior, we can actually interrogate the samples to learn about their stress state. And so the lab tests are incredibly valuable. And then, of course, the drilling data itself provides information about conditions in the Earth as well. In particular, things like the compaction behavior of the materials, porosity, and the velocity, the P wave velocity in the Earth. So what I'm going to do is lead you through 3 case studies where we've done this kind of work, starting at Costa Rica. And this is really focused on the laboratory side of it. Then we'll move to Barbados as an example where we've focused on the drilling side of it. And then the Nankai margin, which is very well studied, but I'll focus on the sort of regional extrapolation part of that. So we're going to start by thinking about the materials that are entrained beneath the décollement, or the plate boundary. And so you can see here, I'm tracing out the sort of reflective surface here is the plate boundary. Everything above this is scraped off during subduction and forms this accretionary prism where we expect lateral compression, and you can see these thrust faults and folds. We'll come back to this a little later. And then you can see this more seismically transparent layer of sediments that sit atop the igneous ocean crust, so that the boundary between the hard rock basement and the sediments is this very reflective layer here. And so you can see there's this stuff like where the blue square is. This is material that is entrained along the top of the slab. And basically, I think of it as lining or directly underlying the plate boundary fault here. And one of the key things about this particular material is because these faults are typically fairly weak, we have a lot of evidence to suggest that in this zone, the vertical stress remains the maximum stress even after the material is brought into the subduction zone, at least in this outer part of the system. And so it begins its life out here in what we call a basinal stress state, where it's just being compacted vertically. And that's essentially progresses here, where now instead of being loaded by sedimentation, it's just got this stuff piled on top of it through tectonic motion. But this material is also still in a condition where the vertical stress is the maximum stress. And so it follows this kind of stress path where sigma 1 is sigma V, and sigma 3 and sigma 2 are the horizontal stresses. And so we can simulate this in the laboratory by taking a sample. And for those of you who have seen me give talks in the distant past, you'll recognize my outstanding PowerPoint animation skills. And so this is basically simulating that vertical burial, a uniaxial burial condition. So you can imagine we're just applying a vertical load and keeping the sample confined horizontally like this. I'll do that again because it's so fascinating, right? So, and so we do this under a controlled rate. And as we do this, what we actually map out is some really simple one-dimensional constitutive behavior. And so what's shown here is void ratio. This is another way of reporting porosity, and it's a proxy for the strain. The x-axis is the log of the effective stress in the laboratory. And so these are 2 different samples where we've, what we see is that initially, as we first start loading that sample, it's just recompressing. It's basically getting back to something that it experienced in the Earth before we went in there and very rudely extracted it by drilling. And then you see there's a change in behavior where it falls along a quasi-linear slope in log linear space here in effective stress. There's been a ton of work on this particular process and problem in the world of soil mechanics and geotechnical engineering. And the basic idea is that if you take a soil or a sediment sample, this point at which you go from a recompression trend to this change in slope is actually representing the material's memory of the largest stress that it has felt in the past. And so you can think of this as grains reorganizing in some way, where everything back here is just sort of elastic, and everything here is it's getting back onto some kind of yielding behavior at stresses it hasn't seen before. And so this is super important because it means that this yellow point here, plus or minus some uncertainty, provides a measure of what the stress is that that sample was feeling in the earth before we took it out. If we also know the overburden stress, in other words, how deeply this sample is buried, we can ask the question, is the sample feeling the total weight of the overburden or not? And if it's not, then that difference tells us what the pore pressure is in the earth. The second thing this gives us is the slope or the form of these compression trends, which provides additional information that basically map between something we can measure really easily, which is the porosity here, and the stress state. And so if we believe these lines, or we can demonstrate that these are consistent over multiple experiments for a particular material, then we actually are armed with a kind of predictive tool where we can measure this easily in a drill hole, and then we can map over to what the stress must be felt in the earth to give us that compaction state. And so there's sort of two pieces to this. And when we apply them to the Costa Rica subduction zone, let's do that first. So this is now the Costa Rica subduction zone, what you're looking at here in the seismic line. Here's the trench. So in fact, this is that photo I showed you with that carbonate outcrop where the fluids are seeping out, is right here where my pointer is. This is a place that was drilled at several locations, one at a reference borehole through the sediments that are overlying the igneous ocean crust before it's subducted, and then at two locations where it's been progressively more subducted. And you'll notice that it may be hard to see in this image here, but actually everything here and here is the same material that's here. So in other words, if you look at the age control from fossils, or if you just count up the total amount of mass, of solid grain mass, everything here is also here, except for the only thing that's missing is water. So this is basically a squeezing experiment, and that's why this is getting so much thinner. It's like a natural compression experiment that's basically the same as this. It's just being done at a large scale and by the earth. And so what I've done here is shown on the right side is our data from a series of samples where we've done these recompression tests down here in the lower part of this site 1040, where it's been subducted now past the trench and is buried by about 300, 400 meters. So this is kind of a shallow example. And I'll just kind of lead you through here. So the what's shown here is depth versus pressure or stress. The gray line is the pressure you'd expect if it's just the water pressure. So that's just the hydrostatic pressure for the weight of the ocean and the pressure exerted by water column. The black line would be the overburden stress. And then this dashed maroon line represents what we expect the pore fluid pressure to be down here if you took this sediment pile and immediately put it beneath this wedge of material. So if you just slid it under here and you didn't let any water out. So you just pressurized that water by the amount that it was loaded. This is so-called undrained burial. That's what you get. And then the blue circles here represent all of those P sub C values where we've interrogated individual samples to ask the question, what stress have they felt? And so you'll notice that it looks like things are pretty close to undrained near the bottom of the pile. And then near the top of the pile, they get something towards something that's like 50 or even 60% drained, meaning this is undrained and this is not overpressured at all, just the static weight of the water column. They're sort of halfway between, right? And so this implies a couple of cool things. One of them is that there is some fluid escape, and it's primarily from the uppermost part of the system. This suggests that there may be upward dewatering, so water fluids are seeping out vertically until they get to either a permeable upper plate or a permeable fault, and then they scoot on out. That's consistent with what we see at the trench, which again was that photo in one of the earlier slides. And then the other thing that's kind of cool is that if you're draining out the top, that means that now another way to think about this is that the effective stress is going to be the difference between the weight of the rock above and the pore pressure. And so the minimum point where the effective stress, that clamping stress, is now the smallest, is by draining, you've actually strengthened this top part of the system because pore pressure has been released. And this point here where my pointer is at 470 meters represents now the new weakest horizon because the pore pressure is closest to the overburden. And so this would suggest that with increasing depth, you may have drainage-mediated weakening or changes in the weakest horizon that could lead to things like downstepping of the plate boundary. And in fact, if you look at the seismic reflection data back here, you actually see evidence for exactly that process occurring with downstepping of the detachment of the plate boundary. Sort of, it basically finds a new weakest zone and cuts off the top half of the sediment section down here. Okay, so this is an example from this again, sort of taking those lab experiments. What I want to do now is kind of move on to the drilling observations. And you may recall I just mentioned this idea that the lab experiments can provide a mapping between, I don't know, my computer's got the rainbow wheel of death here. I think it's just, this is a busy slide. Okay. Mapping between something we can measure, in other words, void ratio or porosity, and something we want to know, which is the in situ effective stress. And so again, key thing here is defining the slope of that line. We did this in the lab experiments with that slope of that line in log linear space. You can also do it through drilling and generate a field compression curve to define that constitutive behavior. And you can do that if you have a reference borehole somewhere that's undisturbed and not yet subducted. And so for Barbados, that's what's shown here. So the trench is about here, or the deformation front is about here. This is the accretionary prism. The red line is the décollement or the plate boundary here. And you can see this is sort of a frontal thrust. And then this is the stratigraphic equivalent going off into the ocean basin. But this is material that has yet to be deformed. And then this is the igneous ocean crust, sort of the gray-black boundary. And so if we take this sedimentary section that's drilled in this kind of boring area that's just on the ocean plate where sedimentation is slow and it's not yet in the subduction zone, that we generate this sort of what we call a reference curve that defines the constitutive behavior. And so these blue dots define that, and then the best fitting line is shown in red. Now what we're going to do is we're going to take this behavior and we're going to use it to estimate what are the stresses and the pore pressures at these 4 boreholes where we're measuring void ratio or porosity through drilling, but we don't know anything about the effective stress. So when we do that, and that's what's shown here, and these sites are now progressively going from closest to the trench and marching further back as we go from right to left. The nomenclature is the same as for the Costa Rica example. So the red here represents the plate boundary fault, and we're in sort of the immediately subjacent material. We have the overburden stress, we have the hydrostatic pressure, and then the maroon dash line is what we expect for undrained burial. So that would be if no fluids could get out at all. And you'll see that that undrained burial line, as we go further back and get buried more deeply, marches to the right. And so in other words, I mean, that should make sense, right? Is that we're getting more and more deeply buried. And if it were totally undrained, the pore pressure would just go up and up and up and up in response to that increased loading. And then what we see is that the blue dots here represent our prediction of that pressure using that relationship we defined at the reference site. So you can see we are documenting what looks like almost undrained behavior all the way back to this point here, which is the farthest point about 8 kilometers from the trench. And this is corroborated at this particular margin by both 2 corks. So these are borehole observatories. The vertical extent here of the measurement is because those wells are zoned. They have a screen that extends for several tens of meters. And so you're averaging pressure over a particular depth window. It's not like it's a single point at like an exact depth. Nonetheless, the cork measurements here and here are really in quite good agreement with, and these are direct measurements, right, are in quite good agreement with those predictions. And then there's also one little white square here, which is a lab experiment of that reconsolidation behavior that also maps pretty closely into these predictions. And so the upshot here is that for Barbados, things are nearly undrained. And that's a consistent story for all three, the sort of multi-pronged approach. And what's interesting is that this is a relatively slow converging. It's only a couple centimeters per year. So the loading rate is actually pretty slow. But nonetheless, we have almost undrained conditions. And this is probably because these materials we know are really clay rich. And so they're probably not very permeable. So it's really hard for the water to get out. It's also interesting just to note, I'll throw this out there, that this particular margin is one that rarely hosts, there are very few, if any, historical large earthquakes. And so people think of this as an aseismic or creeping subduction zone. It kind of comes back to this idea that this extreme overpressure and nearly undrained conditions might help to promote that. Okay, so let's now move on to the case of the Nankai margin. And this is an example. Now we're going to take drilling observations combined with lab experiments and merge them with seismic reflection data to say something about pressure and stress in the upper plate and more regionally. And so one of the observations here, so this is off the Key Peninsula. So this is Honshu here, this is Shikoku Island here. And we're in this sort of in the yellow transect here, which has been imaged and drilled quite extensively. So part of the efforts here were both a 3D seismic reflection survey that documented this sort of lozenge of low velocity material that extends from not too far from the trench, quite a ways to like 45 or even 55 kilometers down dip. And so this is sort of this lozenge of material that's surrounding and in between two major faults, a major splay fault in the system here and the main detachment down here. And so this sort of lozenge of material is on the order of a few tens of kilometers in extent in the dip direction, and it extends a long strike for over 100 kilometers. This low velocity in P-wave velocity, as mapped out by a couple of studies, has been interpreted qualitatively to reflect sediment that must have been loaded so quickly the water couldn't get out. So it's undercompacted and it's highly overpressured. So our goal is going to be to take these P-wave velocities and say something more than just, yeah, it looks purple, looks blue, it must be overpressured, but actually try to quantify what that pressure might be. So the way we do this is we take samples, again, from undisturbed samples of the material that is then brought into the system. So we don't want to take samples of the disturbed material, but also we can't get them because they're too deep. But we can take samples before it gets disturbed, and we torture them in the laboratory. We torture them in a triaxial vessel that at least a couple people who are attending I know have seen or even used, because I was looking at the list of names. Hi, Brett. And so we can simulate conditions up to a few tens of kilometers, 10 or 15 kilometers of burial stress in the lab. And so what we do is we measure a couple of things, and we do essentially two transforms. The first is we want to be able to map this P-wave velocity to porosity. And so we do this using laboratory experiments, right? And so this is P-wave velocity as measured in the laboratory, or on the ship in black, in the laboratory in our experiments in these colors here. And then this is laboratory experiments for exhumed rocks that were buried to 12 to 15 kilometers depth, and they're found now in outcrops, and they're very low porosity and quite high velocity. And so we map out this sort of trend between P-wave velocity and porosity. A key point here is that the P-wave velocity doesn't really care about how you got to a particular porosity. And so these different colors in our experiments are for different stress paths. Some of them were isotropic, so sigma 1 equals sigma 2 equals sigma 3, and others were near shear failure. But regardless of the stress path, the P-wave velocity only cares about the porosity, not how you got to that porosity. So that's a key point. And this allows us to take a P-wave velocity from, say, the seismic reflection data and predict what the porosity is. So that's step one. Step two is that we actually can also map out the compression behavior, much like we did in the previous two studies, where we can now map porosity or void ratio, which is really another way of reporting porosity, to stress or to effective stress. And the key thing here is that the mapping between porosity and stress does depend on how you got there. And so for different stress states, so for the uniaxial case, so this is the gentle vertical burial, as we assumed for the Costa Rica example, you get for a particular mean stress, there's a particular porosity or void ratio. But if you increase the shear stress, and bring the sample to something we call critical state, which essentially means it's pervasively at shear failure everywhere, then there's an additional compactive component, sort of compaction enhanced porosity loss. And so there's this vertical separation between the black and the blue. For our case, because we're in that accretionary prism, when we're near thrust faults like the plate boundary that are active, we assume that we're at or near this shear failure condition where everything is failing in shear kind of pervasively. And that's consistent, for example, with the imaging and the seismic that shows folding and faulting throughout that upper plate. So armed with these two pieces of information, or these two pieces of information and the assumption that we're on this blue curve, we can now go from P wave velocity to porosity, and then from porosity to mean effective stress. And lo and behold, we can then map out what we expect the pore fluid pressure to be quantitatively in this zone of low velocity. And so that's what's shown here. This is work from postdoc Hiroko Kitajima, who worked with me on this project about 10 years ago now. And what's shown here is color coding using the pore fluid pressure ratio lambda, where the redder color is a lambda of 1 means it's pore fluid pressure that is equal to the overburden stress, which would be essentially a 0 vertical effective stress. And the blue color is completely drained hydrostatic pressure. So there's a zone of elevated pore fluid pressure that is interestingly coincides with these low frequency earthquakes that were documented by Sugioka and others in 2012. So that's also kind of another indirect, but now closer correlation and comparison that's quantitative between high pore pressure and these slow earthquake events. And I'll just say, just a sort of a globally speaking, that we now know, and this is work that we've done and that other groups have done, so whether it's the Ecuador margin here, the Alaska margin, the New Zealand margin, other parts of the Nankai margin, high fluid pressure is common. And where we also have done numerical modeling efforts, it's clear that there's really good agreement between independent predictions from numerical models and the estimates from these kind of seismic or drilling predictions. And so we think we have a good handle on this, and the pore pressure in the outer part of these systems is quite high. I'll just say a few words really briefly about this, about how we get those high pore pressures, and then I want to move on to friction. And so just real quick, not going to go into gory detail here, but in addition to the sort of data-driven approaches, we also can construct numerical models that account for the kinematics and the squeezing of this material in 2 dimensions and calculate what the pressure should be in a subduction zone as the subduction is progressing. And when we do this, you can think of it as basically like simulating an underwater situation where we're bulldozing this system, we're squeezing the rocks pretty rapidly, and then how quickly fluids can escape or how overpressured it will be is going to be related to some competition between how quickly we're driving it and how much resistance there is for the fluids to flow, or how permeable the rocks are. And so one of the things that we've shown, or that we've been able to document, is that globally, and I'll take a minute on this slide, globally, we actually see, and so the y-axis here is pore pressure being low, essentially fully drained, up to something that's very high. So the pore pressure up here means that the crust is going to be really weak, and the pore pressure down here means that the crust is going to be really strong. So this is poorly drained as you go up on this axis. And then the x-axis is this sort of competition. It's a ratio between gamma, which is essentially how quickly we're squeezing the rock. So you can think of this, if you ride a bicycle, it's how quickly you're pumping up the bike tire, right? So this is the geologic drivers for pore pressure. In this case, it's things like how quickly the plates are converging. And then this is divided by the hydraulic conductivity. So this is dimensionless, but if it's 1 or greater, then we expect that the forcing is winning relative to the escape. And if this is a tiny number, then it means that the permeability is high enough and fluids can bleed out. And so you can think of this again as a large leak in your bike tire relative to the pumping rate. And so down here, lo and behold, all these black dots are model simulations. If you have small values of geologic forcing or large permeability, you don't expect much overpressure, and then that systematically increases. So it's kind of a generic way of thinking about this fundamental driver of overpressure in subduction zones. And all of the colored boxes are places where we've done this work to estimate what the pore pressure is quantitatively in the earth, and where we know something about the plate convergence and driving rate, and the permeability, because we've measured that independently. And so again, you can see it all kind of follows this trend. And I'll just point out that this is for subduction zones, but you can also put the San Andreas on there, and certain parts of the San Andreas, like where there's mantle devolatilization, and the permeabilities are really low because of serpentinites, we might expect to be up here. And in the continental crust around the San Andreas, where you have faults and fractures that may allow fluids to escape, Town and Zoback in 2001 argued that we're down here in a classic paper called How Faulting Keeps the Crust Strong. And it's really through drainage, right? And so this is a really kind of, I think, a neat universal way of thinking about this problem. Okay, so overall, what we think we know about these systems is that there's really high pore pressure and low stress in the outer forearc. This persists to tens of kilometers from the trench, and it may be part of the story for why we get aseismic slip transients and slow earthquakes out here. Yet it also means that this is weak, and so if you kick it hard enough from behind, it might be easy or it might be able to participate in large ruptures. Okay, so I'm going to skip this in the interest of time, and I want to talk briefly. I told you that I was going to focus mostly on pore pressure, but talk a little bit about friction, just because again, this is sort of, I think, the other side of the coin here, the other side of the story. So I'm going to just show you a couple of quick examples of slip behavior in the outer part of the system. Told you at the very beginning of this talk that we think we know that these are parts of the system that have this transitional behavior, slow earthquakes, slow slip events, and tsunami earthquakes, and talk a little bit about what we know about the frictional rheology that hosts those kinds of things. And so one of the really cool things that we've been able to observe through drilling in those borehole observatories, besides just measuring pore pressure, as I showed you for Barbados, is that time series is also a way of monitoring the creaks and groans of the Earth's crust. And so here is the Nankai margin. We've seen this seismic image before. This is off the coast of the Key Peninsula. And and we have a couple of borehole observatories at this site, C2G and C10A. And in those borehole observatories, the time series of pressure shows something really interesting. And so again, these are, this is an example of what this borehole looks like. So it's drilled into the upper plate. And then we've entombed some sensors down here in the upper part of, or sort of about 1 kilometer deep in the upper plate. And we're monitoring pressure every minute. And we're recording that in data loggers here at a wellhead. For those of you who know her, this is Laura Wallace. You can recognize her by her hair. And what we see in these systems are these spontaneous pressure transients. And so this is now, the blue one is this site here, and then the red one is the site C10. And so there are these spontaneous shifts in pressure that happen simultaneously at two boreholes that are 11 kilometers away from each other. And we interpret these as strain transients that are actually documenting slow slip transients or slip events down here on the plate boundary below that are causing strain in the upper plate. These are accompanied by tremor swarms that occur in the outer part of the system. So here's the trench here. So these tremor swarms are in the outer part of the system. And those tremors actually migrate over time. As that's shown in this upper panel here, where this is distance near the trench is the top and farther away from the trench is at the bottom. And this is day of the month. This is October of 2015. Hopefully you can see there's kind of a slope in this direction. So these are migrating tremor that accompany these strain transients. And so one way to explain the strain transients for this particular event, think of, this one is one that in the first part of this event, let's call it, the blue site here is being tugged on, so the pressure is dropping, it's being pulled apart. The red one is being pushed on, the pressure is going up. So they're opposite sign, but we interpret the red as being in compression and the blue as being in extension. And then later on in time, they're both being extended. So one way to explain this is maybe you have a slip patch on the plate interface down here, and in the first part of this event, this is in the extensional lobe, and so you get this signal here in the blue, and then this here would be in the compressional lobe of that slip event, and it goes into compression. Well, how do we get them both into extension a few days later? Well, if the slip patch moves, that would work. Right now, they're both in extension, and if we had any observations way out here near the trench, we predict, and I can safely say this because we don't have those data, that we'd go into compression there. So we've worked this problem in a little bit more detail to quantify where and how much slip occurs in these slip events. And what we show is that there's pretty clearly migrating slip that occurs over the course of about a week and a half to 2 weeks in the outer 40 kilometers of this system, which I think is totally cool. It's migrating slip. This is distance versus time. The colored curves here are the model fits to the pressure data in black. And then the warmer colors are more slip and the blue colors are less slip. So it's migrating to the trench and petering out in slip as it goes. And when you look at a couple of events where we've done this analysis, what's shown here now is the cumulative slip is sort of timelines. So blue is early in the event and red is late in the event. And so the event is migrating trenchward. And this is the total cumulative slip is the final kind of set of contours here for these two events. These slow slip events, which now we've located with quite high precision, map almost directly into the zone of high pore pressure. They also map directly into patches of the fault out here where we've drilled and we have samples. And so I'll talk about that in just a second. I just want to point out that this is also a zone that's not just high pore pressure, but we have stress measurements from drilling that indicate that this is also a zone of very low differential stress deep in the hanging wall. So it kind of paints this picture of slow earthquakes and slow slip events being related to high pore pressure and low stress, not just low effective normal stress, but low total and low differential stress. Okay, so again, very quickly, because I know I'm going a little bit long here, just wanted to talk briefly about the frictional part of this. And so in the outer part of this system, this is this zone, the outer part of the slipping zone in these slow slip events, where again, we know that the slip is occurring kind of in this whole outer region. We were fortunate enough to drill into and actually sample the fault rocks out here near the trench. So if we take those fault rocks and we shear them in the laboratory to conduct friction experiments on them, what we find, and this is an example of a shear experiment in Matt Ikari's lab in the University of Bremen at Marrum. And then this is you can see these little slicken lines on this for the geologists in the audience. So this is a little sheared sample. What we find is that this rate dependence of friction has a strong dependence on both normal stress and velocity of sliding. And so everything in the bottom half of this plot where A minus B is negative, this is velocity weakening down here. So this is something that would be able to host unstable slip or nucleate unstable slip. Everything up here gets stronger as you try to slide it faster, so-called velocity strengthening. So everything up here above the dash line would be stable. Everything down here has the potential to be unstable at some speed. And you'll notice that the only things that we measure that are potentially unstable are unstable when it's going slow, right? As soon as you try to go faster, it would quench itself. So only things that are slow and at very low stress, 3 or 10 MPa, and that even at 13 to 15 MPa begins to get velocity strengthening. So we sort of restricted the conditions for this material that could be unstable. It can only nucleate something unstable if it's low stress and it's going slow. So hopefully that sounds consistent with some of the other observations. And if we just put this together with a broader set of observations from samples that we've conducted experiments on, or other folks have conducted experiments on. So what's shown here now are the green ones are our samples from that frontal thrust in the Nankai margin. And then the oranger colors, which you can see hopefully are shifting to more rate weakening and more unstable behavior relative to the green ones, are deeper samples from the same rock type. So these are now have undergone some diagenesis, some lithification, and a little bit of pressure solution. And so there's a little bit more quartz in these rocks. And so this offers a hint that maybe there's something that happens with progressive burial that pushes you toward the more unstable regime. That would be consistent with the idea that you have slow, either stable sliding or slow unstable sliding, shallow depth and low temperature. And then you can extend the range of conditions where you get fast stick slip like real earthquakes at greater depths, maybe into that seismogenic zone. I'll just sort of quickly point out that this is not a unique observation to Nankai, but also the Hikurangi margin is another place where we see almost the same kind of thing. And so this is a place where there's also slow slip events that are known to propagate all the way to or near the trench. And this is work that Laura Wallace and others have done over the last decade. And again, this A minus B versus velocity, this sort of trend is also apparent here, where you get velocity weakening and the potential for instability only at low velocities. And so you can only get things going slow. And if they try to go faster, they'll kind of quench themselves. There's also an interesting story here that I'm not going to get into in detail, but happy to chat with folks later, that these materials for New Zealand, at least, also do not heal very much in between the slow slip events. And so this ultra low healing also provides a way to think about how you could get very frequent, like every year or two, and very low stress drop events. And so I'm going to leave it there. But just to kind of summarize, right? So what do we know about these systems? Well, high pore pressure, hopefully I've convinced you, that's the norm in these systems. And the highest pore pressure, where we actually think we know what it is, does seem to correlate with slow earthquake source regions. This is generally consistent with speculation about deep episodic tremor and slip in places like Cascadia and Mexico and Nankai. But we don't know nearly as much about the environmental conditions at that depth. Low healing and the rate dependence of friction seem to be key ingredients for slow slip events. And there's a frictional rheology in the shallow part of the system that lends itself to something that can nucleate unstable behavior if you're not going fast, but it won't let you get fast. And so that's consistent with slow earthquake phenomena through a combination of the low stress and the frictional behavior. And I will happily leave it there and take questions. So thanks so much for your attention. And sorry I went a tiny bit long there.
So please join me in thanking Demian Saffer for this outstanding overview of fault strength and stress and how that leads to interesting behavior on megathrust faults. So now we have time for your questions. Feel free to add your questions on the chat. I'll give you a minute to Demian to catch his breath and everyone to gather your ideas and start posing your questions there. I have one. Actually, I have a few, but let me start with one, Demian.
Sure.
Let me turn on my video here.
Do you want me to leave the slides up, or is it better to?
Yeah, that's okay. So early on in the talk, you mentioned this effect of the high fluid pressure in reducing the critical stiffness and thus leading to more stable slip. And I see this in contrast to the other effect that fluid pressure has that is more obvious when we think about induced seismicity, for example, that you increase the fluid pressure and that takes you closer to failure. So do you think these are two competing mechanisms that might also operate in some sense in megathrusts?
Yeah, it's a really good question. And so, right, when we think about induced seismicity, in some sense, that's I think of that a little bit differently, right? That in order for the earthquake to happen, it still needs to be weaker dynamically than it is statically. And so whether you want to call that cohesion or call it a rate weakening, the pressure is sort of the trigger that gets it to failure by advancing the clock. And so I think of that induced seismicity case as really another version of tectonic loading, right? You're reducing the normal stress, but you could also do that by pushing on the rock and letting the shear stress increase. So you're bringing it closer to frictional failure. So I think that's a little bit different because that's a case where you're not at failure and you're bringing it to failure. But then once you're at the condition of failure, I think this is the mechanism that's going to govern whether it's unstable or whether it creeps. And so there are examples of induced seismicity where or injection where you get creep, right? In certain kinds of faults. And so recognize that this is kind of an oversimplified way of framing it, right? It doesn't account for certain feedbacks or 2D elastic interactions, but it seems to sort of work to first order.
Mm-hmm. I'm going to read one of the questions in the chat. So Bin Hao Wang says, great talk. Could you explain why the high pore pressure region sits in between the splay fault and the Coleman instead of along faults?
Yes. And so, we lack the resolution to say anything about what's happening directly in the faults in terms of the spatial resolution. So that's sort of one issue. We need like a body of rock that is, 1+ wavelengths of the seismic energy thick. The other problem is that particularly for the splay fault, and maybe I can move to that slide real quick. There's a sort of green zone that's actually higher velocity. And this is because, or if you think about this block here has been thrust up by faulting. And that's maybe a little easier to see here. So here's that fault. And so this material here was at one time deeper and has been transported up the fault. And so that means that now it's a much more complicated situation where we can't take our simple approach. And so we've basically avoided that completely because you've had compaction and loading, and then you have like this over stiffened material that's higher velocity, and that our approaches won't work there. And so we've not really tried to get at, so if you notice, that's now in cartoon version, this green zone is this zone up here. And we've cut off our analysis there. So the pressure there could be high, but we don't really have a means to access that without a much more sophisticated model.
I see. I have another question. So you talked about the shallow, slow sleep events and propose this explanation through these high fluid pressures. So I wonder if there are regions or some subduction zones where we know or predict that there shouldn't be such high fluid pressures, and hence are those places where we don't see these slow sleeps, or places where we could instrument to prove that there's no slow sleep to try to get to test your hypothesis there?
Yeah, that's a fantastic question. Yeah, so right, so if pore pressure is a key part of this, I'm gonna I'll just go here, right? So this kind of cartoon, right? Then there are a couple of things that we think should lend itself to low pore pressure. One of them is if you have very little sediment in the trench, right? Then you basically have less hydraulic insulation or impedance, so it's easier for fluids to get out. So those could be places like the Japan Trench, could be places like the western, very far western Aleutians, parts of the Mexican margin, for example, very far northern Chile. So that would be one kind of criteria. And then the other is sediment type. So places where you have more terrigenous, sandy material. And again, parts of the margin off the coast of Mexico may be ideal places to think about that as a potential place. So that, yes, so that's a really good question. One tricky part, and not trying to sound like I'm hemming and hawing or always offering caveats here, but what really controls things is the effective stress. And so you can keep the effective stress low by having pore pressure high so that you're not drained. But if you're shallow enough because the wedge is really thin and there's very little sediment, then even under drained conditions, the stresses will be low just because the burial depth is thin. And so to test this, I would want to go someplace that we think is well drained, maybe because it's more coarse-grained, sandier material, but also it's being loaded quickly enough that we think we'd get high enough normal stresses that we could get it to be unstable. So I would go northern Chile. I would go Mexico. And I'll just point out that in northern Mexico, there are some observations of very shallow aftershocks from the Iquique earthquake.
Chile, you mean?
Or so the Illapel earthquake. Yeah.
Chile.
Yeah, the Chile. Yeah, sorry, the Chile earthquake. Chile margin. Yeah.
Okay. Well, great. That's one place where SZ4D plans to go. So
yeah, it's good news. Nobody even told me to say that.
So along those lines, and seeing you looking into the future, so you showed during your talk many ways in which we can quantify either stress or strength based on things that we can measure close to the surface, and then trying to push to deeper depths, maybe down to seismogenic and even tremor depths by using geophysics or using models. So what's the future of that? Where do you see that there are opportunities to maybe develop new methods to try to do these inferences deeper or better, or
Yeah, I think one key thing is the world of laboratory experiments. So there, for the deeper part of the crust, there's a lot of work, like Nick Christensen in the 70s and 80s and 90s did a huge amount of work on the velocities, P and S wave velocities of different rock types. under different stress conditions. And so, you know, that's kind of like a library at our disposal. But what's been done less is taking rocks that have been through the deformation processes in subduction zones that have been recrystallized, have strong foliation, and looking at the anisotropy and making those measurements at even higher, you know, pressures, that's been accomplished, but at higher temperatures that hasn't. And so I see that kind of calibration exercise in a way is much more challenging in the laboratory, but it's not impossible. And that would be a way to explore, for example, if the high VPVS ratios that are inferred from receiver functions or from active source surveys in the deep ETS zone, what do those really mean? And are they uniquely telling us something about pressure or stress for the rocks that we think are down there? And the rocks that we think are down there are not intact isotropic Etna basalt, right? They're something else. But we know now through efforts like GeoArray, for example, that are planned, how we can go to places that would be relevant to get the right rocks. So I see that as a really important step. And then the other thing would be to bring in joint constraints from electromagnetics. And so that's something that's not, it's sort of in its infancy in some ways in terms of trying to get the higher spatial resolution and also calibrate and map that to fluid content.
Yes. Well, thank you, Demian, so much for your insights and for answering all these questions. I don't see more questions in the Q&A chat. So I think, well, please, everyone join me in thanking Demian again, and hope to see you all again tomorrow for the continuation of these webinars and workshops.
The next webinar is at 5 p.m. Pacific time today, and it's Dr. Jim Morey will be giving that talk. So thank you all again for coming, and thank you, Demian. And we hope to see you very, very soon.
All right, thanks, everyone.